Everybody, Mr. Gatlin here, going through Math Models, Chapter 2, Section 1. Make sure that you've got your pencil, that you've got your book, that you've got your paper, because you are going to need to have the things that I'm going to tell you in this lecture to use on the homework. So just be prepared, make sure you take good notes. Chapter 2 begins with this example from forensic anthropology. So chapter 2 starts out with this idea of someone has discovered some bones and they want to figure out some information about the person from the size of the bones. Now some people have got bigger bones, some people have got smaller bones, things like that. But from the perspective of math models, what we want to do is figure out this general trend, this general pattern. How can we predict what will happen? In chapter 1 we studied concerts and things like that, and we're just not capable of knowing exactly how a business transaction is going to work out. We're not capable of knowing exactly what's going to happen with this. However, what we can do is make a model that's going to predict what will happen approximately. And that's what we're looking for, is an approximation. So at the end of this, you will be able to use models of the form y equals mx and evaluate their accuracy by using residuals. So two things we're going to be able to do. The first thing is you create models in this linear form. That's what y equals mx is called. It's the linear form. And we're going to be able to use these, and again, this linear, excuse me, I got slightly off there. We're going to use this form right here. And this is called linear. You're going to be able to use the linear form to predict things, and you're going to be able to evaluate how accurate your linear model is by using something called a residual. Okay, so those things together are what's going to give us our understanding here. Okay, so as we move along, in chapter 1 of your book, it starts out again with this example of Amelia Earhart, actually, and how they believe that they may have discovered her bones. And how do you know? Well, they measure the length of her leg bone and different things, and they calculate a European woman of a certain height. Now, so the project type thing in this chapter is the same thing. There's a group of hikers, and they found some bones. All this information is given in your textbook on page 70, but I've got it up here on the screen for you also. Now, they found 3 femurs with lengths 41.5 centimeters, 41.4, and 50.8. They found 1 tibia, 1 ulna, 2 ulnas, all these different things, and a number of fragments. Now, we understand immediately the fragments are not going to be particularly helpful for us in discovering any information about the person. A bunch of little pieces from 3 to 5 centimeters long, not very helpful. But all these other things can be very helpful. In your book on page 70, you'll see on the left side a chart, an anatomy chart that's got what bones have what names to give you a sense of what we're looking at. So the first thing that it tells us is, if you look at the data in the table, the team reported that they belong to at least 2 people. How do they know for sure they belong to at least 2 people? Look at that for a second and think about it, and you realize it's here. How many femurs did they find? Your femur is the top part of your leg bone. How many legs do you have? You've got 2 legs. So if they found 3 femurs, there must be at least 2 people. Now when we look at the length of them, and one is 41.5 centimeters, one's 41.4, and one is 50.8, we can immediately see these 2 belong to the same person, and this one was someone else, in all likelihood. So it's this combination of things that allows us to start to make some conclusions. Now, the book asks us, what bones belong to which person? Sort of call it skeleton 1 and skeleton 2. So we kind of reason about it a little bit, and I'm going to bold skeleton 1, the smaller person, and we'll italicize skeleton 2, the the taller person. So 41.6, the length of the tibia. If you look at the picture in your book, you'll see that the femur appears to be about the same length as the tibia. Maybe the femur is a little longer, but this probably still belongs to the same person. The ulna, the forearm type bone, is considerably shorter, and so but there's, maybe that would be confusing, except there's two of them. See, so 22.9 is the smaller one. 29 definitely doesn't belong to the same person, so the 22.9 will be on our skeleton 1. The radius here, 21.6. Again, your radius matches up with your ulna, the two different forearm bones. So certainly somebody with 29 centimeters on one wouldn't have 21.6 on the other. Kind of reason your way through this. Humerus is the top part of your arm, 35.6. By that, it sort of summarizes what we've got so far. 35.6. That's quite long, and so somebody with a 21-inch forearm is not going to have a top of their arm that is 75% longer. They're about the same, and so it'll be the taller person. The complete skull, maybe we don't have the information for that at this point, but I'm just going to go ahead and say the complete skull. A 23 centimeter skull seems like it probably belongs to the shorter person. Now, the next thing that your book asks us to do is to guess, are they male or female? And I don't think that we can do that immediately, but if we jump down to part E, guess the heights of the dead people, maybe we can do that. Can we guess the height of the shorter person? Well, if I add their lower leg bone, their upper leg bone, their lower arm bone, their upper arm bone, and their skull, that's not going to really give me their height. I'm skipping their feet and their I'm skipping their feet and their neck and things like that, but it'll give me a decent approximation. So let's do that. If I just picked one on these ones where I've got multiple bones in roughly the same place, if we did the tibia starting at the bottom, plus the femur, plus the ulna, plus the humerus, plus the skull, that's going to give us a decent approximation. Now, the person will, in all likelihood, actually be a little taller than this, but it gives us something to work with. So if I add those heights up together, I get 159 centimeters. Now, 159 centimeters is 5 foot 3 inches. So the person is probably going to be a little taller than this, but 5 foot 3 will work. Now, I would probably guess then that somebody who's 5 foot 3 is going to be female, and so that gives me something to work with immediately. Now, part D of question 1, do you think the dead people were young children or adults? Well, if the shorter one is 5 foot 3 at least, and there's someone who's taller than that, then it's very, very unlikely that they're children. So we'd say they're probably both adults. So this team has found 2 adults, one smaller, about 5 foot 3, one quite a bit larger. And so without knowing the larger person just yet, one thing that we can say immediately is it's probably a man and a woman. An adult man and an adult woman. Now, one thing that we know that your book's going to tell you is that artists use this rule of thumb, where when drawing a teenager, for example, they say that the size of the body is the head times 7. Okay? You can sort of check that out with yourself. You measure your head and you measure your height and see how close that works for you. So if we use the skull now, the skull is 23 centimeters. I multiply that by 7 and I get 161 centimeters. Now, I add up the bone lengths and I get 159 centimeters. That's awfully close. In fact, that's probably closer than we would think. Closer than we would think because we expect our estimate to be kind of low. But in any case, 160 centimeters, still about 5 foot 3 inches is what both estimates give us. Okay, so 7 times the skull size. This is a model of the form MX. Okay, so Y, the height, equals the skull height, which is our X, times M. In this case, M is 7. So based on the teenager metric, if I know that you are that your skull is a certain number of centimeters, I can multiply that by 7 to get your height. This will also, of course, work in inches. So this is a very simple model. Now, one thing is, it's one of the characteristics of a linear model like this, y equals mx, is that it passes through the origin. What does that mean? That means that no matter what, it always goes through the point 0, 0, which is what we would expect for this kind of thing, because if your skull is 0, your body is 0. If you've got a small skull, here you'll have a small body. As your skull gets bigger, your body probably gets bigger also. So these two models, the adding up the bone lengths and 7 times the skull size, both put us in the same place. There again, we can see where those numbers came from. And now we can be fairly sure at this point of this 23 going with the smaller size, since the estimates line up so closely. Now, based on that then, I want to know the height of the bigger person. Well, the bigger person, I don't have very many bones to work with. I've got their femur, I've got their ulna, and I've got their humerus. But I don't know anything about their tibia, I don't know, their radius. So I could go with this a couple different ways. One technique I could use is say, well, for the smaller person, the femur is about the same length as the tibia, so this is probably going to be about the same length here. I do have an ulna. For the radius is just slightly shorter than the ulna, so I could call this 28. And then I don't know the skull, but this would give me a ballpark to work with. But I don't want to go that exact route. What I'd rather do is set it up as a proportion. And I'd say, okay, I know that skeleton 1 has a femur that's 41.5 centimeters, and skeleton 1, by my estimates, is 160 centimeters tall. I get that by meeting in the middle. You see, I had 159 and 161. So by meeting in the middle, I say about 160. Now, I know the femur is 50.8. And the height, I don't know. I want to solve for that. So what I'm going to do here is I'm going to cross multiply. You're familiar that if you cross multiply 41.5 times x, 41.5 times x here, equals 50.8 here times 160 here. Okay? That's where that equation comes from. Now I do a little math. I multiply 50.8 times 160 in my calculator to get 8,128. I divide both sides by 41.5. I'll give you a second to write that down. And then in my calculator, I just do that division. Of course, the 41.5 cancel, and I'm left with x equals 196. 196 is 6 foot 5. So just going based off the femur, which we understand is not the standard model, it's not the skull size, but we didn't have a skull. Just going off the femur and assuming a proportion there, I get 6 foot 5. So even if that's not very accurate, this is still a man, and that gives us an estimate. So I'd like to say, it asks us in E, how accurate we think our height guesses are. I'd like to say that the smaller person will be fairly accurate. The taller person will be considerably less accurate because we had to put together several guesses to arrive at a solution. Now, if we continue to play with that, then maybe in general we want to know how our model works. So just working now on this idea of residuals. If I, in your calculator, I want you to add a new page. I want you to set that new page to lists and spreadsheets. I hope tomorrow I will be able to get the calculator to display on the screen. Lists and spreadsheets. Now in the very top column of each, I want you to write these words. I want you to write actual on the first list, predicted on the second list, and residual on the third list. And just fill in these data points that I made up. Skip the second one, of course, that's where you'll put equations, and leave residual blank for the time being. But plug in actual, predicted, predicted. And actually, do not plug in these numbers. There's a mistake here. I corrected it here. So we're going to have to skip ahead a little bit. Plug in 140 for your actual, 175, 156. And then for your predicted, plug in 138, 181, and 154. Now go over one more column and go to that second one that's kind of grayed out and click variable or press variable and select actual, minus, press variable, and select predicted, and then press enter. If you don't use the variable, then you can actually type it out with the small keyboard at the bottom. You can use that keyboard to get to type the word actual minus the word predicted, and it'll still work. Your calculator will recognize that as a variable. Now 140 minus 138, I made some changes here, and that's of course not what your calculator will say. Your calculator will say 2. I made some changes and they didn't come through. It will say 2. 175 minus 181 is negative 6. And 156 minus 154 is 2. So I don't know, this must have been from some numbers I had used before. So that gives me my residuals, 2, negative 6, 2. Now in a well-balanced equation, in a perfect world, your residuals will add up to 0. When will the residual be positive? Well, the residual will be positive when the actual result is higher than what you predicted. When will the residual be negative? When the actual result is lower than what you predicted. So a good model will overestimate sometimes and underestimate sometimes, but it'll about even out. In this case, I've got 2 that are positive and 1 that's negative, just because I don't have very many data points. But 2 plus negative 6 is negative 4. Plus positive 2 is negative 2. So my model is fairly close to 0. So it's not a bad model, whatever this model is. And these are residuals. Now if that number were huge, then we'd have a problem. If that number, were even smaller, if that number were 0, then I'd say, oh, I must have the best possible model. So those residuals are something I want to minimize. If my residual is way large, then I want to change my equation to be a better equation. So you see how these different things fit together. You see how if we're going to have models, we can't just guess something and then sort of pretend. We've got to really have a way to know if our model is any good or not. Because if we're whatever you're doing, if you're in business, if you're a scientist, if you're whatever, and you really want to have a model, you don't want to have a model just for the sake of having a model. You want to have a model because you want to actually know stuff. And so you need a way to tell if your model is good or not. And residuals are the real life way that we do that. Okay? Now, the book goes on to tell you that artists, when they're drawing adults, do not use 7, they use 7.5. So if we were going to estimate this person's height again, we would say 7.5 times the 23 centimeters of the skull gives me 172.5 centimeters. Now, the same kind of basic idea as we go and we look, there's different things you can do, but the 172.5 centimeters is 68 inches. Well, 68 inches then is of course 5'8". So that gives us somebody who's a little taller. Probably still a woman. 5'7". Probably still a woman, but taller still. So that gives us some sense of a more accurate estimate. And that makes more sense. The original estimate was too close to adding up the bones. We expected it to be a little higher. And of course that compares to this. So last thing, here again is our model, y equals mx. We've tried this two different ways. We've tried y, which is the height, equals 7x, where 7 is the constant and x is the size of the skull. We've tried y equals 7.5x. Now, if you play with this graph, or with graphing, and I ask you to plot y equals x, it'll look like this. If I ask you to plot y equals 2x, it'll look like this. If I ask you to plot y equals 10x, it might look like this. So what m does is m, which is called the slope, controls the steepness. You know, if you are on a steep slope, that means that it's very sharp. If m is large, it means it's very sharp. If the line is straight up, then that means that the slope is undefined. You could never climb it. If it's flat, the slope is 0. It's not steep at all. Now, slope, and we will talk about this more, but I want you to write it down, is equal to delta y over delta x. Delta is the Greek letter for D, for difference. It looks like a triangle. And that just means the difference in the y's, which is you just subtract them, over the difference in the x's. One other way you might have heard this is rise over rise. So that's it. That is a linear model. A linear model means it's got some kind of slope times a variable that predicts another variable. Your height is like that. Your height, there's some number where I multiply it by your skull and I'll figure out your height, approximately. I can tell how good my slope is at predicting that based on the residuals. If the residual is larger, and if I have two numbers and one has a larger residual and one has smaller, then the one with the smaller residual is more accurate, and that's the one that I should favor. So all these things together give us an understanding of what we ought to do. Now, a little bit of practice work for you on pages 76 and 77. I want you to do numbers 1 through 6. So all this comes together. You know that you can use these artist guidelines to figure these things out, to use a linear model to predict someone's height based on the size of their skull. You know that you can use data to see how accurate your predictions are by calculating residuals. And you know that you can tell me if one model is better or worse than another by looking at the residuals. All those things are very useful. All those things are very important. And I wish you the best of luck on your work.